Good afternoon, ladies and gentlemen. My name is Todd Longendorfer. Welcome to the fourth session within the Connexus webinar series. Today I will continue where we left off from SIL selection and move on to SIL verification and conceptual design. Following your SIL selection process, you will have obtained a required SIL for a given function. And what we wish to establish in this presentation is the methods in order to determine the performance available from a given function. To give a little bit of an introduction myself, my name is Todd Longendorfer. I've served as a staff engineer here at Connexus for the previous 4 years. My work as of late has been within validation and verification activities for clients in the Southern United States as well as the Gulf of Mexico, in addition to several international clients. I also have certification as an ISA 84 SIS Fundamental Specialist, and I received my degree from the Ohio State University as a Bachelor of Science in Chemical Engineering. What we will cover in today's webinar is once again a continuation from the previous webinar on SIL selection, and we'll look at the role of SIL verification within the safety lifecycle. We'll also examine the factors that affect the safety performance, and also determine safety availability and unavailability. Also to be covered are the failure modes of our field devices, as well as diagnostic coverage and its role in safety availability. And then lastly, we'll take a look at fault-tolerant criteria required to meet the demands of higher SIL applications as noted within IEC 61511 and 61508, standards from the International Electrotechnical Committee. Within the SIS design lifecycle, once again, the verification phase typically occurs after selecting your SILs for your given functions within the safety instrument system and prior to the development of your specifications and your procedures. What we'll look to establish in this phase is take the SILs obtained from SIL selection and then determine if the safety instrument system is capable of meeting the requirements set forth within the SIL selection portion of the process. And as mentioned, what we wish to do is to quantitatively verify that the selected equipment and the testing is capable of meeting the requirements. What this will involve is using calculations in reliability engineering. And throughout the analysis, we'll take a look at the safety integrity level that is achievable by a given function. And as seen from the chart available here, we note that the safety integrity level is determined on a number of factors. Component selection only comprises one part of the achieved SIL. Other notable factors include the frequency of your functional testing conducted, common cause failures that have the potential to feed redundant devices within your system, the amount of diagnostic coverage available, as well as the degrees of fault tolerance present in the function. To recap briefly safety integrity level, you can view safety integrity level as several bands ranging from 1 to 4, and each is a measure of the safety availability of the function. Another way to look at it is in terms of its probability of failure on demand, which is the inverse of the safety availability. And further, we can also define the safety integrity level in the form of a risk reduction factor, which takes our probability of failure on demand, takes 1 over the probability of failure on demand to establish a number, which is a little more concrete than the percentages listed here. Know that, though, typically a SIL1 function ensures approximately 90% safety availability, and then each SIL higher than SIL1 provides roughly an order of magnitude better than that safety availability. So we began today by looking at the definition of failure, which is the most basic concept within reliability engineering in general and safety instrument systems engineering. At its most basic level, failure is the lack of success, but trying to define that within itself is difficult because of the variety and complexity of failures. It can occur in a variety of ways and result in a multitude of effects on the system, ranging from extremely dangerous to inconsequential. By defining the failure in terms of the lack of success, all the different failure modes and the effects are going to be neatly combined into a single package. Now, looking at the opposite side of this, you may wonder what is success. Success is performing an intended function within the desired targets of acceptability. What we need to consider when looking at an SIS is the capability to perform an intended function whether or not the system is called upon to do so. The probability that the system perform or is capable of performing the intended function is the probability of success. Now, it's important to note that when it doesn't perform the action intended, then the system is not considered to be performing successfully. And each of these topics will be addressed in further sections ahead. When gathering failure data, we can obtain that data by two means. We can take a look at test data or performance data. With test data, we are concerned with data obtained from control tests of a device. Usually, this contains a very large representative sample size and is very useful for academic purposes and demonstrating the fundamental principles and relationships. However, the data may be presenting information within applications that are relatively, as mentioned, controlled and may not be applicable to the subject environment. Performance data is data obtained from the actual performance monitoring of the installed equipment. And usually this tends not to be as robust as that of the test data. And unless the sample size is relatively, or rather adequate, then it may not be appropriate in terms of making meaningful decisions and assessments. To give you a definition of the failure rate, we'll take a look simply at the failure rate as being a measure of the number of failures over the mission time of the instrumentation. And as far as reporting the failure rate goes, we typically refer to this in terms of failures per hour. As you see in the example here, we have listed 5.2 failures per million hours, which we would then convert in scientific to 5.2 times 10 to the minus 6 failures per hour. We may also choose to refer to these in terms of failures per billion hours, and this is typically known as FITs, short for failure units. So using the previous example, we would define this as 5,200 failures times 10 to the 9, or 5,200 FITs. Now, if we take a plot of the instrument failure rate and measure it against its expected lifetime, we'll notice a tendency for the instrument to have significantly higher failure rates near the beginning and the end of the lifetime. This is not unexpected, as over a large sample of device, several devices will fail relatively early in the phase to the left, which you will see as the infant mortality phase. Similarly, over to the right, we have the wear-out phase, where devices will tend to fail more as the device approaches the end of its useful life. So therefore, in determining the average failure rate of the instrument, we'll primarily be concerned with how the instrument behaves over the period within the middle range, the useful life of the device. And this also prevents the failure data average from being biased with respect to the high rates that you might see within the infant mortality and the wear-out phases. With performance data, as mentioned, the component lifetime will be relatively short compared to that of the data that you may be able to establish within a test. The failure result is typically expected to result in a repair or replacement, and ideally the device will be replaced before the component fails, before it reaches the wear-out portion of the operating life cycle. And you may have to take special consideration for multiple operating environments and process services. When we take a look at performance data and try to use that to establish failure data for a given component, what we'll be concerned with is the results that we obtain within our periodic functional test to determine the hidden failures of the component, as well as the maintenance records, which will help us identify spurious failures. In determining an overall failure rate, we will take a look at the periodic test and the repairs, and note the number of failures within each of the events. We will combine those failures and then compare that against the total time of the equipment, and that will be based upon the periodic test data. From there, you should be able to calculate failure rate based upon the number of failures and the equipment time, as you see here, subdivided into failures per year, hours, millions of hours, or bits as you see fit for your particular application. When data is scarce, you may wish to establish a confidence limit for your instrumentation, noting that the mean value will often give you the desired value, but in lack of more robust data, this may not be enough. So IEC 61508 recommends that you set a value slightly above that of the mean, which will capture 70% of the expected values. This will result in a higher failure rate than the mean, but will be more conservative and likely to be more accurate with the expected true behavior of your instrumentation. So we move on to reliability engineering, which is the discipline of analyzing and quantifying the failures in order to prevent the effects of device failures. What we'll be taking a look at specifically is the components and the systems that comprise the SIF. We start by defining reliability of a device. This is the probability that the device will properly function over a given time interval, not taking into consideration the ability to detect or repair the failures. So as provided by the equation below, reliability will be equal to e to the negative lambda t power, where lambda represents the failure rate and t represents the time interval. Of importance, you'll want to make sure that the failure rate and the time interval are in the same units of measure, as reliability will be given to you in unitless quantity. Using the following example here, a typical pressure transmitter with a failure rate of roughly 3 minus 3 failures per year and a time interval of roughly 5 years will result in a reliability as listed below of 0.983 or 98.3%. Similarly, you have unreliability considered within a device, and this is the probability that over a given time interval, your device will fail to function properly. As you see from the equation below, it is simply the opposite of reliability, 1 minus r, or 1 minus e to the negative lambda t. And using the same example we had before, where we had 98.3% reliability, to determine the unreliability of the instrument, you would simply take 1 minus that quantity, which would give you 0.017 or 1.7%. Notably, where the failure rate is low, however, the unreliability can be approximated with a more simple expression. We simply state that the unreliability will be approximately equal to lambda over t, providing as noted in the caution that the unreliability is not greater than roughly 0.1. Now, moving on from reliability and unreliability, there will be several terms to establish with respect to mean time, and we'll take a look at that in the slides up ahead. We'll be concerned with mean time to failure, the mean time between failures, the mean time to repair or restore, and the mean downtime of the instrument, which takes into account both the time to repair and the time to detect the instrument. And as you note here, we mentioned that the time to detect will be roughly half of that of the diagnostic test interval. Now, taking a look at a repairable system, the typical behavior that we expect of the instrument is that it will operate until it reaches a state of failure. This was demonstrated by this first term here, TTF1, or the time to failure. Following that failure, the system must be repaired and has an associated time to repair, the quantity TTR1. The sum of these components is noted as TBF1, or the time between failures, knowing that you cannot have a failure once a failure has occurred. And over the lifetime of the instrument, you should expect that the instrument will experience several similar patterns of time, failure, and downtime. And it's these averages of these occurrences that we'll use in order to determine the mean values of failure and repair time for the devices. And also to consider during the time of repair, as mentioned before, is the amount of time it takes to first detect the failure before repair, which is added on to the time, the total downtime. The mean time to failure, then, for a constant failure rate system can simply be taken as the inverse of that failure rate, or 1 over that failure rate. We'll be using that in the equation up ahead in terms of availability, which we consider as the fraction of the time that a repairable system is in the operational state. We look at that as a view of the system's uptime versus the system's total time, which, as presented below, is the mean time to failure over the mean time between failures, MTTF, plus mean time to repair, MTTR. So using the example of a thermocouple that has an MTTF of 7 years and a relatively short MTTR of 24 hours, we see that a component with these requirements will have an availability of roughly 99.96%. Conversely, you have unavailability for an instrument, which is the fraction of time that a repairable system is in the failed state. The unavailability, as before with reliability, unavailability being the complement of availability. And so in this equation, we're concerned primarily with the mean time to repair and how that compares versus the total time of the device. So we can look at Q as being a measure of 1 minus the availability, 1 minus A. So taking the previous example we had, Q will be simply equal to 1 minus the availability of the instrument, which will be roughly 40 minus 4. Now, similar to reliability, unavailability also has a rough approximation as long as the unavailability is not expected to exceed 0.1. We can simply state that the unavailability will be roughly equal to your failure rate times MTTR. So we tie this into PFD, or probability of failure on demand. This is simply the likelihood that an SIS component will not be able to perform its safety action when it is called upon to do so. PFD manifests itself as a result of dangerous failures, and you can calculate this as a result for a point in time or over a time interval. So for the sake of calculating the achieved SIL of our functions, we will be concerned on the average probability failure of demand. Sometimes this quantity will be based on unavailability and sometimes unreliability. And what this depends on is the availability to test within the mission. If failures are detectable or repairable mid-mission, we can use unavailability. But if it is not, we must use unreliability. And with respect to defining the SIL, we can more easily define it perhaps in the terms of a risk reduction factor, or RRF. This simply represents the number of times that the risk will be reduced as a result of applying the safeguard, and is typically more convenient for describing a system's effectiveness, although this is only valid for preventative systems, not mitigating systems. So in concern for PFD average, what we'll want to look at is how to calculate it. What we note is that it's an increasing function of time, at least with respect to unreliability. The average PFD can be calculated over a given time interval, and what we'll be concerned with is that average, which is an integral of a continuous function of unreliability divided by the time period. And this will help us to establish the PFD average as noted in the SIL levels for ISA 84.01. What we establish then, based on the definition, is an approximation for PFD average, which will be roughly equal to lambda times the time interval of interest over 2. And in the case of unavailability, the PFD average will be roughly equal to that of lambda times MTTR. This may look similar to the approximation for unavailability as presented earlier, but as you may note, unavailability is already by definition average over many time intervals. In order to understand how events are related, we have to provide a definition as to probability. With concern to probability, we're looking at the possibility that an event will occur as expressed by the ratio of the number of actual occurrences to the total of possible occurrences. It will fall somewhere in between 0 and 1. With respect to independent events, an independent event will be an event where the outcome does not depend on past events or other concurrent conditions. And within reliability engineering, we typically assume that the failures of the devices will be independent events. On the other side of that, there is complementary events, where we consider two potential events that can occur in a situation that are not possible to occur simultaneously. Failure states, whether it be failed or operational, are typically assumed to be complementary. Where these are concerned, the probability of the event, of the complementary event, will be equal to 1 minus the probability of the other event. And expanding from that, we can also consider mutually exclusive events, where an event may have not two, but multiple potential outcomes, where one of the outcomes must occur, but other outcomes are not possible simultaneously. And the sum of all the probability states is 1. So when combining the event probabilities, we can combine them under the principles of two events occurring at the same time, or the possibility of either of two events occurring. So for the first case, we have a case where an event will be true if A and B is true. In this case, you multiply the probability of the event, probability of A times probability of B. In the case of an event being true, whether A or B may be true, you go ahead and add the probability of the events and subtract the product of the probabilities of those events. And the general form of the OR example is listed below as 1 minus a product of 1 minus the probabilities considered. With respect to probability addition, though, the product of the two probabilities in relation to the sum of the two probabilities is expected to be relatively low. So typically within our calculations, we'll simply state that the probability of A or B occurring is roughly equal to the sum of these components. As before, the probability error may become significant once you exceed 0.1, so caution should be observed when using this approximation. The same logic can be applied to events. When considering an event that may occur based on another condition, you will use an AND gate and take the event frequency multiplied by that conditional probability. In this case, the frequency of A times the probability of the event occurring to come up with a frequency B. In the case of two events being considered with OR logic, you would add the frequencies of those two events, frequency of A and frequency of B, to obtain a sum frequency. And there are several ways to model these logic relationships. Several of these methods include the fault tree analysis, the Markov analysis, the reliability block diagrams, and simplified equations. Markov analysis is typically not used for these applications, as it is a very complex and time-consuming process. Within fault tree analysis, you calculate the likelihood of a given top event resulting from several basic events that work logically to make the top event occur. The basic events are related to that top event through the logic gate. And using probability frequency principles as mentioned earlier, we use the frequencies or the probabilities of the events under to calculate the frequency or probability of the top event. The strength of the fault tree analysis is that this is the most flexible approach in terms of conducting, in terms of fault modeling, and you can model sequences of failures. The process is relatively self-documented and easily understood. However, it has some limitations in that in some simplifications that are used within the fault tree, those could result in errors, and they're typically more time-consuming than that of simple equations. Another example is reliability block diagrams, which takes the reliability of the system from looking at a side on the left and moving to the right. Where you have an AND relationship, you have a series of blocks, and where you have an OR relationship, you have parallel blocks. You use probability math in a similar manner as to fault tree analysis to simplify the blocks into a single event. And the strength of this system is that it's easy to understand and perform and relatively self-documenting, much like the fault tree analysis. However, one of the limitations that occurs in this is that being a reliability block diagram, it's limited to the probability of success, and it can be difficult to use in determining the failure probability associated with multiple failure modes. Lastly, we have simplified equations, which provides the easiest method and a highly accurate method of solving of fault propagation modeling. And software and spreadsheets may be available for these equations. But the limitations of this method is that not all the situations have an equation that fits the situation, or sometimes that selecting the appropriate equation may be difficult due to multiple equations being available for a given situation. The devices that you will be examining throughout SIL verification will have several failure modes associated with the devices. These are considered as conditions preventing the device from performing its intended function. And you'll note that most instrumentation have multiple failure modes, and each of those failure modes may have different effects. What we'll be looking at throughout our analysis is those effects that may occur as a result of the type of failure that you are looking at. We have those failures which are diagnosed as safe, or overt or initiating failures. These failures cause the SIF to perform the safety action, although a hazardous condition may not necessarily exist. Opposite that, we have dangerous failures, or covert or inhibiting failures, which prevent the SIF from being able to perform the action upon demand. And lastly, there are also no-effect failures or residual failures that neither inhibit nor initiate the SIF action. The percentage of safety within the device determines the performance of the device, and no-effect failures when looking at this percentage should not be included and are not relevant to the SIS engineering. Now, ISA 84 defines a term as safe failure fraction, and it's important to note that what we define as safe failure percent here may not necessarily be the same as that, but we'll discuss that a couple of slides ahead. Now, in terms of the overall failure rate, based on what you have available to you, and noting several modes of failure will be safe and others dangerous, you can subdivide this failure rate lambda into several components, lambda S safe and lambda D dangerous. Here we have the example of a level switch, which has several failure modes. We note that, however, that the failure to function is dangerous, but the availability of the level switch to function without a signal is safe. And several unknown failures will be associated with level switch 2. When this occurs, it is typically considered conservative to split the expected failures that may occur as a result of being unknown. This allows us to develop failure modes and effects analysis, or FMEA, for components. What we have here is the level switch and the listed failure modes, and we defined each of these failures in terms of whether this failure mode will be an inhibiting action, an initiating action for the SIF, or whether we'll take a split of the value as noted before in the unknown values. So whereas before we may have had a total failure rate as listed below of 1,400 fits, now we're able to subdivide some of those failures into safe failures and some of those as dangerous. And we'll note that from this particular example, we have a safe failure percentage of 39%. Now, as mentioned before, as we look in our reliability calculations, we will be concerned with a term called safe failure fraction, which looks similar to that of the percentage of safe failures within the system. However, this fraction looks at the overall hardware failure of the device that could result in either a safe failure or a detected dangerous failure, and compares it against the total failure rate. This plays a part where diagnostics are concerned. With diagnostics, we'll be able to periodically test the SIS at a rate more frequent than that of the overall test interval, and these tests can be conducted typically automatically and online. What this will enable us to do is convert some of the failures that would otherwise be dangerous into safe failures by causing a shutdown of the system, which will allow for faster repair of the system and, in essence, shorter mean downtime and lower unavailability. Several means of diagnostics are available and vary with your instrumentation. The device may, for instance, use a reference target to detect abnormal conditions and move the system to a safe state, such as reading an off-scale high-low signal or taking the reading from the output and using that within the input. The device may also detect, for instance, an incorrect response during a desired action. Logic solvers may compare the results of a system with multiple components and move the process to a safe state if there should be, for instance, a disagreement in voting or communication. For software, a watchdog timer can be used to detect a certain amount of time of inactivity from the system, at which point the software will take an action to safely shut down the system. And certain instrumentation will also contain built-in and custom-developed diagnostics, which may be provided by the vendor or the manufacturer. Now, with respect to diagnostics, we can develop two additional terms, coverage safe and coverage dangerous. These will be the fraction of failures that can be detected by a given set of diagnostic tests. And as mentioned, this allows you to develop further failures that are both safe and perhaps detectable or undetectable, and failures that are dangerous detected or undetectable. And as you see, this allows us to expand on our previous definitions and now come up with 4 lambda terms for our devices: lambda SD, lambda SU, lambda DD, and lambda DU. For a given component, you can take either of 2 methods in defining the failure characteristics of your device. You may choose to use each of the 4 subdivisions of failures: safe, detectable, safe undetectable, dangerous detectable, and dangerous undetectable failures. Or you may choose to define them with the column on the right. As a failure rate, a safe failure percentage, which, as mentioned earlier, is a measure of the safe failures over the total failure rate, and the coverage and the diagnostic coverage available: dangerous and safe. So, using another example here of a pressure transmitter, where we may have had several failure modes before that were diagnosed as dangerous, with diagnostics available to us, we can take those failures and monitor whether or not those failures have occurred to the logic solver by detecting an analog signal. For instance, in this case, a pressure transmitter is being used in high trip service, which is safe when the component fails high, but is dangerous when the component fails low. If the logic solver, for instance, however, is able to monitor a signal of under 4 milliamps for the pressure transmitter, indicating a low failure, then the logic solver can take the means to diagnose that failure and safely shut down the process. So continuing from that, we can develop a more thorough FMEA with the help of diagnostics, and we refer to this as the Failure Modes, Effects, and Diagnostics Analysis, or FMEDA. So with these failure modes, we'll have listed out the failure modes and the effects of these failure modes as listed before. And now we'll also include a column over on the right side here of the failure rate, which will define whether those failure modes are detectable or not, and the diagnostics available in order to detect those failures. So this would allow us to obtain a safe failure fraction of 74%, where, as available before, if we did not have diagnostics available to us, we would have only the safe failure percentage of 14%, the amount of safe failures available to us without diagnostics. You can also use the FMEDA, or Failure Modes, Effects, and Diagnostics Analysis, as a means to determine the failure characteristics of multiple components. In this manner, you would go ahead and systematically analyze every system component and quantify the performance of your system based on the quality of your components. In order to meet the higher SIL requirements, as noted in IEC 61508 and 61511, your systems need to have some measure of fault tolerance. And this will be the ability for the system to perform its intended action in the presence of a failure. Specifically, you'll be concerned within redundant components of whether or not those components have safe and or dangerous fault tolerance as required by your particular application. We'll take a look at several voting arrangements to help us gain a grasp of what are the effects on the PFD and the STR, as well as the degrees of fault tolerance available for those voting arrangements. So here, first of all, we have a 1 out of 1 voting arrangement. Simply one vote to trip out of one device will cause your shutdown action to occur. And the equations for these are the ones established as seen earlier with PFD average, and as you'll note, STR, which is equal to lambda S plus lambda DD, provided that dangerous detected failures will enact a safe shutdown. If they're not, you'll have to add an additional term to the PFD equation, and this is noted below. This arrangement has neither safe or dangerous fault tolerance. With respect to detection, we'll look at, with respect to how this plays an effect within our PFD average calculations and STR calculations, we'll take a look at each of the failure modes available to us. In the case of safe detected failures, if it's configured for shutdown, a nuisance shutdown will occur, and the system will be in an available state. However, if it's configured only for alarm and not shutdown, a safe detected failure will cause the system to be unavailable. This is also similar for the dangerous detected case noted in the third row below. A safe undetected failure is expected to always result in a nuisance shutdown, or not unavailable state. And conversely, a dangerous undetected failure is expected to always result in an unavailable state. Now, different responses to the detected failures require different equations to be used. And specifically, ISA TR 84.02 equations assume that your detected failures will result in a shutdown. So you may need to take special consideration in cases where that is not the case. Another common voting arrangement seen is a 1 out of 2 voting arrangement. We look at this as an arrangement where one vote to trip out of 2 possible devices will cause your shutdown action to occur. As seen in the example here, this has a dramatic effect on the PFD average provided here. But with respect to the STR, now we provided an additional instrument that is capable of shutting down safely in order to enact the shutdown action. And as a result, since either component can shut down safely in order to initiate the action, your STR doubles. This particular arrangement then has 1 degree of fault tolerance, dangerous, but none safe. The opposite of this would be the 2 out of 2 voting arrangement, where 2 votes to trip out of 2 are required in order to initiate the shutdown action. You have 1 degree of safe fault tolerance as opposed to the previous arrangement before, and that now your system will not safely shut off unless both of the devices have done that, have initiated the action, which helps significantly lower the STR with respect to the 1 out of 1 arrangement. But now that we have added 2 devices into the equation, now we must require both the devices to shut down the equation. So as opposed to the 1 out of 1 voting arrangement, your PFD has doubled. The 2 out of 3 voting arrangement seeks to gain some balance between the 1 out of 2 and the 2 out of 2 voting arrangements by providing both a degree of safe fault tolerance and a degree of dangerous fault tolerance. In this voting arrangement, 2 votes to trip out of 3 devices will cause your shutdown action. And you'll note in the last row below that neither the PFD nor the STR are the most optimal values, but in this case, both of the values are better than that of the 1 out of 1 voting arrangement, which cannot be said in the case of the 1 out of 2 or the 2 out of 2 voting arrangement. But as far as redundant systems are occurred, there exists the possibility for failures to occur in 2 or more separate channels, in a multiple channel system, which will result in failure of all the instruments considered. And these are considered as common cause failures. With respect to common cause failures, we'll be concerned with a beta factor, which is a fraction of the total failure rate that results in all of your components considered within a redundant system to shut down at the same time. We can view this as setting a common cause failure rate of beta times the overall failure rate. Estimating this beta factor can be provided through ISA TR 84.02 or IEC 61508 methods. These standards typically provide a value of 0.5% to 5% for logic solvers and 1 to 10% for field equipment. Now, IEC 61508 Part 6 Table D4 provides a more thorough analysis of the beta factor for various devices and helps you establish that beta based on multiple factors such as separation, diversity of the components, the working environment of the component, available procedures, and so forth. From this analysis, a net score is calculated based on a checklist of yes or no questions, and this will help you to determine the beta for your particular process. Once you have established this common cause, incorporated into the analysis is just as simple as simply applying it to the analysis once all the redundant groups are considered. And in terms of calculating this in terms of PFD average and STRCC, you will take the common cause failure rate and use the equivalent 1 out of 1 vote-to-trip equations for both PFD and STR in order to calculate this value. And once you have established the PFD and also following from that STR for each of your components, then combining the data just simply involves taking each of the subsystems and summing them together by probability addition. This will be the sensor subsystems, the logic solver subsystems, and the final element subsystems. As mentioned before, a minimum degree of fault tolerance may be necessary at higher SIL levels. What the minimum fault tolerance will be for each of your groups will be dependent on the required SIL of the function, the safe failure fraction of the function, and in some applications, as defined in IEC 61508, the type of device. IEC 61508 defines these types as either A, being a simple device with well-understood failure modes, or B, a more complex device such as microprocessors. Defining the minimum hardware fault tolerance within ISA 80.61511 for sensors and final elements is based upon the SIL level provided. For each SIL level of 1, an additional degree of hardware fault tolerance is required. The requirements for SIL 4 are specifically defined as a part of IEC 61508. For logic solvers, you have the ability to certify the logic solver for certain SIL that you would not otherwise be able to obtain with sensors and final elements, providing that your safe failure fraction is good enough for the application. For instance, in a SIL 2 application, if your logic solver meets a safe failure fraction of over 90%, then no additional hardware fault tolerance is necessary. However, if it falls in the region below 60%, then you may need additional fault tolerance as listed in the table. As previously, SIL 4 is a requirement identified in IEC 61508, and so special requirements exclusive to that standard apply. With respect to IEC 61508, it defines the minimum fault tolerance in terms of the safe failure fraction and the required SIL. For type A devices, a safe failure fraction of between 60 and 90% may enable a single component to obtain a SIL of 2 without any need for additional components. With type B, the requirements are a little more stringent, however. In the same application, you will need a safe failure fraction requirement of 90 to 99%, in order to ensure that a single device without any hardware fault tolerance could be used in the SIL 2 application. If it fell in that 60 to 90% band, for instance, then you would be restricted to SIL 1 with respect to that instrument. To develop more concepts with respect to minimum fault tolerance, there also exists a means of lowering the minimum fault tolerance through the use of defining the equipment as demonstrated as being in good prior use. For all subsystems except for programmable electronic logic solvers, you can reduce the minimum fault tolerance by 1 if the devices used comply with all the following below, and that the hardware selected is based on prior use, that the device only allows process-related parameter adjustments, and that the adjustments are reasonably protected, and that within your particular application, the required SIL is less than 4. The components that you will use in your subsystem must meet the requirements of SIL 1 to SIL 3 in being in accordance with IEC 61508 parts 2 and 3, i.e. being certified for use for those SIL levels, or be selected based on prior use. You cannot use prior use, however, as a means of ensuring that components may be certified for SIL 4 applications. In this, you have to ensure that the components are in strict accordance with IEC 61508. Your prior use requirements may also vary on the programming language that is required for the given device, whether it be a programmable piece of equipment with fixed programming language or limited variability language. In the case of FPL programmable components, you'll want to ensure that the unused features of the components are analyzed and determined to be non-interfering with respect to the device being able to perform the required safety action. And you must demonstrate that the component has experience in a similar operating profile. Namely, you should monitor the characteristics of your input and output signals, the modes and the functions used, and observe its use within a similar application and physical environment. And additionally, for SIL 3, you will also need a formal assessment. For components with limited variability language, you'll want to demonstrate that the component has sufficient experience within the same operating profile, considering the SIL of the SIF and the complexity of the functionality. For SIL 1 and SIL 2 particularly, you'll be concerned with the device having understood unsafe failure modes, and since most of these components involve logic solvers, having a safety configuration to address known failure modes. You'll want to ensure that the embedded software has good history and that the device is reasonably protected against unauthorized modifications. For SIL 2, additional requirements are demanded in terms of a formal assessment. So, for the sake of this presentation, you'll want to consult IEC 61511, Part 1, Clause 11.5.5.6 for this assessment. And lastly, you'll want to make sure, within terms of prior use, to document the requirements considered, the qualitative requirements considered in developing the data, as well as the basis for the quantitative parameters used to select the failure rate for the component. As defined before, IEC 615 recommends setting a confidence level of around 70% in order to ensure that the value is not too favorable with respect to the data that you have recorded. Alright, and that effectively includes the webinar. The main points we want to establish from today is that for your given system, that you want to ensure that your PFD average is suitable for the required SIL. You'll want to ensure that the spurious trip rate for the process and your SIP are reasonable so that you don't incur excess nuisance shutdowns. You'll want to select components that either meet IEC 61508 certified requirements or prior use requirements. You'll also want to note that SIP Diagnostics will enable some of your dangerous failures to be detected and move the SIP to the safe state, and that fault tolerance requirements may be necessary in higher SIL requirements, as noted in IEC 61511 and 61508. Alright, and that effectively includes today's webinar. Thank you for attending today. If you have any particular questions with respect to this, I can be reached at my email address, simply todd.longendelfer@connexus.com. Thank you for attending, and have a good afternoon.